Hello again everybody. In today's video, we're going to be talking about Lagrangians in classical mechanics. Now we use Lagrangians to figure out the changes within a system. For example, we might want to derive an acceleration equation that then might let us get the equations of motion with respect to time. Or maybe we want the equations of motion with respect to angles. Lagrangians are super diverse, and that's frankly what makes them a little bit difficult to learn. So first, let's just introduce what are Lagrangians. So to start us off, your Lagrangian is going to be equal to the kinetic energy minus the potential energy. That's pretty simple. Now what we do with this Lagrangian equation is we convert that with an Euler-Lagrange equation. Now first things first, let me just write the whole thing down, and then let's take it step by step to see what every single term means. This is going to be our Euler-Lagrange equation. Now first things first, let's go through every single variable just to make sure that we understand what's going on here. This first term means that we are going to take a derivative of this stuff inside with respect to time, and this is going to be for every single variable inside. So let me just repeat that. We're going to take a derivative of every variable that is inside. Now I emphasize that because you might need to brush up on some calculus or some chain rules. Because for example, if we have something that looks something like this, d dt, and let's say we're going to take the derivative of some position and some velocity, these are going to be with respect to time, so we're going to have x dot, the first derivative, the derivative of the position, times the velocity, plus x times the derivative of the velocity. So you might want to brush up on your calculus and your chain rule, because every variable with respect to time can be taken a derivative of. Now the second term, dl over dq dot k, this just means that we are going to take the derivative of the Lagrangian, whatever this stuff up here is, and that is going to be with respect to whichever variable you want q dot to be. For example, q could just be the position x, and then q dot could just be the derivative of the position. Now this little k term comes into play is if we're dealing with multiple objects in a system, and we might need to classify them as the position of the first object and the derivative of the position of the first object, when compared to something like x2 or x dot 2 of a second object in the system. And last but not least, this final term over here is just going to be taking a derivative of your Lagrangian up here, and that's going to be with respect to qk. Again, q is just any variable, and again k is just to distinguish which object within that system, if it has multiple variables of the same term, or that are being called the same. Let's try to look at a few examples that can be solved using regular Newtonian mechanics, so that we can see what their applications are in terms of Lagrangian mechanics. Let's start off with a simple example of a pendulum. So we have a mass that's hanging on a string of length L at some angle theta. Well, for our Lagrangian, we need to find the kinetic energy and the potential energy. For the kinetic energy, we know that it's just going to be 1/2 mv squared, but we don't know the velocity. However, we do know that it depends on the derivatives of the position. So to clarify myself a little bit more, it's just 1/2 m, the derivative of the x position squared, plus the derivative in the y position squared. Our next task is to find out what the heck is x and y. Our x position is going to be equal to the answer of this right triangle over here. That's L sine theta, and of course for y, that is negative L cosine theta, because I have noted that up here we're going to say that y is in a negative direction for this problem. Now here's where things get a little bit tricky, the derivative in the x position is going to be equal to L cosine theta times a theta dot. I'll get back to that later. And then in the y position, that's just going to be L sine theta and another theta dot. Now let me go off on a tangent and explain myself. So if we were to do a derivative of something like d theta of sine 2 theta squared, something that looks around like this, we would get cosine of 2 theta squared. That's the easy part. And then we still take d theta of the stuff that was inside. And of course, this is just 4 theta times cosine 2 theta squared. So just to drill this in your head a little bit further, if we take the derivative with respect to time of the variable theta that can change, something as simple as this is going to be cosine theta, and then we still need to take the derivative with respect to time of theta. That is how we get our cosine theta times this theta dot. So when you do these Lagrangians, you have to be really careful about how you approach taking derivatives with respect to time. Alright, back to the problem. So our energy is going to be 1/2 m x dot squared plus y dot squared, that's in parentheses. And once you do all the math here, I'll skip through that to save some time. It's just going to be 1/2 m L squared theta dot squared. And if you're still wondering why it's this, well, another tangent, cosine squared theta plus sine squared theta is equal to 1. And that's how you can just simplify it a little bit further. And finally, our potential energy is going to be mgh, and that is just negative mg L cosine theta, because h is just y. Alrighty, now we have everything to find out our Lagrangian. Our Lagrangian is just this little guy. Now let's find every single term and our Euler-Lagrange equation, starting with dl over d theta. That's just going to be negative mgl sine theta. dl over d theta dot is going to be m L squared theta dot. And lastly, d dt of the thing we just did, that is going to be m L squared, and remember that we're taking a derivative with respect to time. This just turns out to be theta double dot, the second derivative. We can finally plug in everything that we've gotten so far and come up with the solution of m L squared theta double dot plus mg L sine theta is equal to 0. And one sneaky little trick that you can do is say that if theta is a small angle, approximately 0, you can also say that sine theta is equal to theta. That's a neat little trick. And finally, simplifying one last time, we're going to get theta double dot plus g over L theta is equal to 0. And we end up with a solution that is a second order ordinary differential equation. And I have a video on that can help you solve through these types of equations. And from here, you can find the equations of motion with respect to theta as a function of time. Let's do one last example to illustrate a different point. Let's look at a mass that's going down an incline at some angle theta. Well, with Newtonian mechanics, you can just simply find the acceleration going down the slope to be g sine theta. So, if we try Lagrangian mechanics, we should also end up with the same answer. The one thing that I want to illustrate with this problem is that you do not always need to find out the equations of motion with respect to the x and the y position. For example, since the mass is just going down this slope, in this section over here, and we want the acceleration in that specific direction, we can say that this position is just dictated by the position r down the slope of the ramp. So the position is just r is equal to r, its derivative, r dot, is equal to r dot. So if we say that the kinetic energy is equal to 1/2 mv squared, well, the velocity, or the derivative of the position, is just equal to 1/2 m r dot squared. And finally, the potential energy is equal to mgh, where h, if you just solve with SOHCAHTOA, is mg sine theta times r. And finally, we can add both of these to solve for the Lagrangian. And from here on out, it's just a bit of tedious math, so I'm just gonna speed run my way through the math. Well, now that we have all of our derivatives taken care of, let's solve for the Euler-Lagrangian equation. Once we do that, we're going to end up with mg sine theta minus mr double dot is equal to 0. And rearranging this one last time, we're going to get r double dot is equal to g sine theta. And that's exactly the result that we get from Newtonian mechanics. The acceleration that the mass is going down a slope is equal to g sine theta. Again, I used this example just to illustrate that you don't always need to separate the x and the y position. Sometimes you could even simplify it into just the position of where the mass is going, regardless if it's a combination of the x and the y position. But of course, every problem is unique and should be taken care of accordingly. I hope this video helped you guys out, and good luck out there.